Hi everyone! Welcome again to my channel, Math is Fun channel. This channel is an educational channel to help you understand about your lessons in mathematics. And also this is intended to those who are doing the online classes out there and also those who are answering their modules. This is very helpful for you to really develop your learnings in mathematics. So please do not forget to subscribe my channel and of course share this channel to those who are struggling in mathematics because this will help them realize that math is not a difficult subject. It's easy, fun and interesting, and also this will help them to improve their performance in mathematics. So please do not forget to share this video discussion to your friends out there so that they will also learn about math. Is that great? Yeah, that is so awesome. A very good advocacy to share my knowledge about the people who are struggling in mathematics. So I hope you're going to support my channel and please continue to watch my video discussions because you will make your life productive in mathematics. So are you ready in our next video discussions? I guess you are very excited for our next topic in this video discussion. So our topic in this video discussion will be about properties of real numbers. I know that we encountered about real numbers before, but we will focus on the properties of real numbers in this video discussion. So I hope you're going to focus on the properties of real numbers. So let's start. Okay, to start with, of course, the properties of real numbers is our main concern in this video discussion. And of course, we have to be guided with the standard and also the objective. For the standard, we are going to apply algebraic order of operations and the commutative, associative, and distributive properties to evaluate expressions and justify each step in the process. Okay, that is so exciting. And of course, your objective in this video discussion is to apply order of operations to solve problems by applying the properties of real numbers by performing the correction operations using math facts, skills, and writing reflective summaries. Are you ready? Let's get started. Okay, to start with, we have to um, remember or review about the terms that we have there on the screen. The word set notation rather, natural numbers, whole numbers, integers, rational number, irrational number, and real numbers. So when we say, so to review, let's have first a review about the word set. We all know in our previous discussions that set is a collection of objects, correct? And aside from that, there is a set notation, as you can see. That's the symbol used to represent a set. And natural numbers are counting numbers from 1 to 3, so on and so forth. And of course, we have whole numbers, natural numbers, and zero. Of course, when we say whole numbers, we include zero. But for natural numbers, we don't include zero. So these are the vocabularies that we need to remember in this topic or in the subsets of real numbers. Okay, so we have there the integers or the word integers. We defined it as positive and negative natural numbers and zero. So examples, as you can see, -2, -1, 0, 1, 2, 3, so on and so forth. And we also have rational numbers. We define rational number as a real number that can be expressed as a ratio of integers or fraction. And of course, we have the irrational numbers or irrational number. It is defined as any real number that is not rational. So example of it is the square root of 2 and pi. And of course, our family, our mother in this in the terms that we have the word real numbers. So when we say real numbers, all numbers associated with the number line. So again, we define real numbers as all numbers associated with the number line. So the word set notation, natural numbers, whole numbers, integers, rational number, irrational number, and real numbers. These are the vocabularies that we have to remember in mathematics. Because in mathematics, we encounter these numbers, especially in algebra. Okay, not only in algebra, in all branches of mathematics. So I want you to remember these words so that you can recognize them, and it will be easier for you to communicate with them. So let's continue. So our essential questions in this video discussion is to, how do you know if a number is a rational number? So this is part of our essential question in this video discussion. How do you know if a number is a rational number? Another, what are the properties used to evaluate rational numbers? So let's continue. So there are two kinds of real numbers in algebra. So we have it, the rational numbers, and we also have irrational numbers. These are two types of real numbers. Take down note, okay? So rational numbers are numbers, as I defined it a while ago. A rational number is a real number that can be written as a ratio of two integers. It is a rational number written in decimal form, is terminating or repeating. Again, when we say rational numbers, a rational number is a real number that can be written as a ratio of two integers. And of course, a rational number written in decimal form is terminating or repeating. Okay? So we have here the examples of rational numbers. We have it 16, 1/2, 3.56, -8, 1.333, -3/4. And of course, the next example, or another type of real number, is irrational number or irrational numbers. So we define irrational numbers as a number which is a number that cannot be written as a ratio of two integers. In short, you cannot write it in the form of A over B or in a fractional form. And if a number is cannot be written in the form of A over B, then we can say that it's an irrational number. Okay? So that is understandable, right? So another definition for irrational number: irrational numbers written as decimals are non-terminating and non-repeating. So in short, irrational numbers can be non-terminating and non-repeating. So as you can see, square roots of non-perfect squares. These are irrational numbers. Again, square roots of non-perfect squares are irrational numbers. So we have the example, pi, another, square root of 17, and of course the pi, okay, an illustration of a pi. So now we can now represent a real number or real numbers in a Venn diagram. So we all know that a real number is a system, or it has a family. So what are the family or families of real numbers, or the subsets of real numbers? So real numbers consist of natural numbers, as you can see, example 1, 2, 3, so on and so forth, where 0 is not included. And of course, another, whole numbers. Natural numbers are part of whole numbers. However, in whole numbers, we include 0. And of course, they are under the family of integers. So integers are part of real numbers, and also natural numbers and whole numbers are part of integers. Example, -11 and -5. And of course, integers are part of rational numbers. So in short, the subset of real numbers are rational numbers, integers, whole numbers, and natural numbers. Of course, we have to include the irrational numbers as part of real numbers. So the subsets of rational numbers, we have integers and non-integers. And the subsets of integers, as you can see, we have the whole numbers and natural numbers. And the subset of whole numbers are natural numbers. So the Venn diagram will help us understand about the subsets of real numbers. We call it the real number system. So now let's proceed. So real numbers, as I have said, we have the natural numbers, whole numbers, integers, and of course, we have the rational numbers. And of course, the other one, I did not write, that's irrational numbers, the empty uh, diagram. Okay, so now we can say that real numbers consist of rational and irrational numbers. And under rational numbers, we have its subsets, the integers and non-integers. And also under integers, we have the whole numbers and counting numbers. That's it. Of course, we have to consider the negative and the positive numbers and also zero. Okay, under integers. So rational numbers. Okay, so natural numbers are natural counting numbers like that example where zero is not included. For whole numbers, as a review, natural counting numbers and zero. Example 0, 1, 2, 3, so on and so forth. And of course, the integers, we have the whole numbers and their opposites. And of course, we have here the rational numbers, integers, fractions, and decimals. These are part of the rational numbers. And of course, okay, making connections on it, biologists classify animals based on shared characteristics. The horned lizard is an animal, a reptile, a lizard, and a gecko. Rational numbers are classified this way as well. So as you can see, so that's how we relate rational numbers in other field of subjects like science. So real numbers, okay, same as how I've shown a while ago. So this diagram represents a real number. So reminder, real numbers are all the positive, negative, fraction, and decimal numbers you have heard of. All numbers that you can imagine. Those are part of real numbers. All numbers that you can imagine that can be found in a number line, because there are numbers that cannot be found in a number line. We call it complex number. Okay, so do not forget that one. They're also called rational numbers, the real numbers. Okay, and irrational numbers are usually decimals that do not terminate or repeat. They go on forever. Examples: the pi, square root of 2 and square root of 3. So properties, let's now go over with the properties of real numbers. It's very important because we can use it in algebra, especially in solving an equation or simplifying an expression. So a property is something that is true for all situations. So these are the rules that we can use in solving or simplifying an expressions or equations in algebra or in the world of mathematics. So again, a property is something that is true for all situations. So we have four basic properties of real numbers. We have the distributive property, commutative property, associative property, identity properties of 1 and 0. And of course, we also have to include the inverse property. So we commute when we go back and forth from work to home. So the first property will give us this idea. So algebra terms commute when they trade places. So example, this is an example of commutative property. For addition, x plus y, yeah, y plus x. In short, according to commutative property, even if you interchange them, then nothing will change. In short, x plus y is equal to y plus x. That is according to commutative property of addition. So there are two types of commutative property. The first one is commutative property of addition. As you can see, x plus y is equal to y plus x. Okay, so Commutative, this is a statement of the commutative property for addition. As I have said, x plus y is equal to y plus x. And another thing also, commutative property does not only work rather in addition, but also for multiplication. So it also works for multiplication, as I have said, correct? So now we can also represent commutative property under multiplication as this. Xy is equal to yx. So even if you interchange them, they are just the same or equal. So properties of addition and multiplications for the words commutative property, you can add numbers in any order. That is the concept of the commutative property of multiplication and addition. So again, as I have said for a while, as I have said, when we say commutative property again, you can add numbers in any order. You can multiply numbers in any order. The order cannot be an hindrance for you to change its answer or result. Example, this one, 3 plus 4 and 1 half. Then you change its position, 4 and 1 half plus 3. And also 2 times 17 is equal to 17 times 2. Again, the concept in here is you can add numbers or you can multiply numbers in any order. That is according to commutative property of multiplication and rather addition. So in algebra, we can represent it as a plus b is equal to b plus a for commutative property under addition, and ab is equal to ba is under commutative property of multiplication. And the next property that we're going to study on this video or in this video discussion is about associative property. So what's associative property? When you are only adding or only multiplying, changing the grouping will not affect the sum or product. So same with commutative property, associative property has two types. We can have associative property of addition, and we can also have associative property of multiplication. For the concept of associative property, as I've read a while ago, changing the grouping will not affect the sum or product of the numbers or the expressions that we have. Example, 6 plus 8, it's grouped, plus 9 is equal to 6 plus the quantity of 8 plus 9, where 8 plus 9 is grouped or changing its group rather on the right side of the equation. But it's still the same thing. It will not affect the result. Let's see. 6 plus 8 is 14. 14 plus 9 is what? 14 plus 9 is 20. What is 14 plus 9? 14 plus 9 is equal to 23, correct? Again, 8 plus 6 is 14, plus 9 is equal to 23. And then in this side, 8 plus 9 is 17. So 17 plus 6 is 23. See, they are just the same. Nothing will change even if you change the groupings. So this property is a proof, or it tells us that even if you change the groupings or the parentheses, the result will not affect, or the sum or product will not affect or will not be affected. So same in multiplication. 2 times 1, 8 times 16 is equal to 2 times the quantity of 1, 8 times 16. So changing the grouping will not affect the sum and product of the expressions or numbers. So in algebra, this can be, or associative property of addition can be represented in the symbol a plus b, where a and b are grouped, plus c is equal to a plus the quantity of b plus c. And also for associative property under multiplication, this is the algebra symbol, or it can be represented in algebra as this: A times B, or A, where A and B are grouped, and multiply it to C is equal to A times B times the quantity of B times C, where B and C are grouped. So this is an associative property under multiplication. So I hope we are clear about this one, the commutative property and also the associative property, both under multiplication and addition. So now let's proceed to the next, distributive property. So when we say distributive property, it tells us about the word distribute. We distribute the expressions or the numbers. As you can see, A times the quantity, you read this one rather, as A times the quantity of B plus C. You distribute A to the parentheses or to the expressions being grouped. So A times B, so we have AB plus A times C is AB, and A times C is, it must be A, sorry, typographical error. So that should be AC. Again, A times the quantity of B plus C is equal to AB plus BC. So this is how you do distributive property under addition. Addition or subtractions, it depends, but it doesn't matter at all. We take it as one property, namely distributive property of multiplication. So distributive property of multiplication applying in this given, solving for real numbers, we have 4 times the quantity of 3 plus 5. So we distribute 4 times 3, as you can see, 4 times 5, as you can see there. Then that's how you do or apply the distributive property of multiplication over addition. So I hope you will be able to grasp the concept about this lesson or property. It's easy to remember about distributive property of multiplication. Another, so commutative property of addition and multiplication, as I have said a while ago, order doesn't matter. So A times B is equal to B times A, and A plus B is equal to B plus A. And of course, to associate with someone means that we like to be with them, correct? So just like that, the dogs, they want to socialize or associate with their same bloodline or same category. So the tiger and the panther are associating with each other. So as you can see, they are leaving the lion out. Okay, so in algebra, we can just like or apply that, the lion and then the panther and the tiger in associative property in groupings. So x plus y, where x and y are grouped, plus z. So the panther has decided befriend the lion. So the tiger is left out. So it can be also have it or equal to x plus the quantity of y plus z, where the y and z are grouped. In short, when quantity x plus y, close quantity plus z is equal to x plus the quantity of y plus z. So that is the meaning of the associative property. In short, this is a statement of the associative property. As you can see, as I mentioned a while ago, quantity x plus y, close quantity plus z is equal to x plus the quantity of y plus z. In short, the groupings will not affect the sum and then the product of the expressions or numbers. So the variables do not change their order. Okay, so the associative property also works for multiplication, as I have shown rather a while ago. I had shown rather. So xy, where x and y are grouped, times z is equal to x times the quantity of y times z, where y and z are grouped. So it's the same as that. So associative property of multiplication and addition, as you can see, associative property for multiplication, we have A times B times C, where A and B are grouped, is equal to A times B times C, where B and C are grouped. So example, 6 times 4 times 3, where 6 and 4 are grouped, is equal to 6 times the quantity of 4 times 3. So as you can see, even if you multiply it, yeah, if you're going to show it, of course, 6 times 4 is 24, correct? This is 24 times 3. That gives you what? 72. And next, in here, 4 times 3 is 12. Then 12 times 6 is 72. Yes. So they're just the same also. Correct? So this is what I said a while ago. The groupings will not affect the result. Same in addition or associative property in addition, this one. So 6 plus 4 is 10, plus 3 is 13. Then in here, 4 plus 3 is 7, plus 6 is also equal to 13. So they're just the same. So see, this property will tell us that the groupings will not affect the result. Okay, so I hope you'll be able to grasp the property or the concept of this property. And of course, the distributive property that no one for addition and one for multiplication. Again, not one for addition, but one for multiplication because both operations are used in one property, yes. This is an example of the distributive property. As you can see, we distribute 4 times 2x, this one, sorry. Okay, for a while. Okay, I have to annotate. So this one, 4 times 2x, that gives us 8x. 4 times 3, that gives us 12. So that's how we do the distributive property of multiplication. Okay, so 8x, and then we have 4 times 3, as I've said, plus 12. And of course, here is the distributive property using variables, x, y, sorry, x times the quantity of y plus z is equal to xy. We distribute x to the expressions in the parentheses. We have it x times y is xy, x times z, xz, correct? So I hope you'll be able to grasp it. So that's it. That's the distributive property of multiplication. And another thing also that we need to remember is the identity property makes me think about my identity. As you can see your face in the mirror, or, yeah, on the mirror rather, then you will see yourself, of course, not the other self. Okay, so the identity property for addition asks, what can I add to myself to get myself back again? So, like that. So, what will you add to your x to make you or to give you an answer or a result of x? Of course, that's 0. So 0 will make it or will give you, yeah, will give you back again, just like x plus 0 is equal to x itself. So that's what we call identity property. Okay, so the above is the identity property for addition. So when we talk about identity property for addition, then we think about 0 because all numbers that will be added to 0, the answer will be the number or the expression itself, correct? That's why 0 will give you the identity as a result when you add it. When we talk about identity property for addition. Yes. So 0 is the identity element for addition. So again, 0 is the identity element for addition. Please take down note of that. And of course, if we have identity property for addition, we also have the identity property for multiplication. Ask, what can I multiply to myself to get myself back again? Of course, it's obviously 1. All numbers and expressions that will be multiplied by 1 will be the number and or expression itself. So meaning the above is the identity property for multiplication. So 1 is the identity element for multiplication. Do not forget 0 is the identity element for addition, and 1 is the identity element for multiplication. Yes, exactly. So we can define the property as this formally. If you add 0 to any number, the number stays the same. As I have mentioned a while ago, a plus 0 is equal to a, or 5 plus 0 is equal to 5. If you multiply any number times 1, the number stays the same. A times 1 is equal to A, or 5 times 1 is equal to 5. And of course, let's have an example, identity properties of addition and multiplication. Name the property that is illustrated in each equation. Negative 4 times 9 is equal to 9 times negative 4. What do you think? Huh? What do you think? Okay, so that's it. The order of the numbers change. Therefore, we are applying here the commutative property. Yes, exactly. Very good. Okay, so that's it. We apply the commutative property, sorry, of multiplication in letter A. What about in letter B? Go on. I'll give you time. Okay, so letter B, it gives us what? Okay, the factors are grouped differently. Okay, so when the factors are grouped differently, then it tells us about associative property of addition. Yes, exactly. Okay, so I hope you'll be able to grasp the concept about this lesson or in this activity about the properties of real numbers. So I hope you will be able to remember this. So solving equations, 5 properties of equality. We have the reflexive, symmetric property, and transitive property. So when we say reflexive, for any real number, a a is equal to a. So do not forget, again, these are the 5 properties or properties related to equality in solving equations. I will introduce this one in equations or in solving linear equations. So again, I will just include this one in this in the properties of real numbers because this might help in the future rather. So we have it there. Reflexive property means for any real number, a is equal to a. Yes. For symmetric property of equality, for all real numbers a and b, if a is equal to b, then b is equal to a. That is symmetric property of equality. And for transitive property, for all real numbers or reals a, b, and c, if a is equal to b and b is equal to c, then a is equal to c. Yes. So please do not forget about the theorem or the properties for reflexive, symmetric, transitive properties of equality. So I hope you're going to take down note of that. So of course, let's have an example. Using the commutative and associative properties, simplify each expression, justify each step. For this, of course, you're going to have it 29 plus 37 plus 1 is equal to 29 plus 1, which is easier to use, plus 37 is equal to what? Yes, we apply the commutative property of addition in here. Then after that one, we can group it 29 plus 1 plus 37. Then that gives us associative property of addition. So next, we got this one, 30 plus 29 plus 1 is 30 plus 37. That gives us, then add 67. Okay? So I hope you'll be able to remember about the concept. So the properties. So this one, let's have an exit slip. Name the property that is illustrated in each equation. For number 1, what do you think? Okay, that is associative property of addition. For number 2, we have it. What? Okay, so we have it 6 times y times 7 is equal to Yes. 6 times 7 times y, that is commutative property. Exactly. Of multiplication. For number 3, 8 times 11 times the quantity of 11 times 1/4, that gives us 22. And of course, 4 times 90 is 392. And number 5, 7 times 32 is equal to 224. So that's it. So that's how we do it. Okay, so that ends our discussion about real properties of real numbers. And another thing also, I guess I forgot something. Yes, I forgot something. So I'll just write it in a whiteboard. So we also have one property that I missed. I'm so sorry. The word inverse property. So I'll just write it. Inverse property. So according to this property, of course, this property is categorized as under multiplication and under division. Of course. So for multiplication, the inverse property of multiplication states that the product of any number and its multiplicative inverse is 1. So example, A over B. Of course, what will be multiplied to A over B to give you a multiplicative inverse of 1? Of course, it's reciprocal. Yes, very good. So we can multiply it as B over A. So see, when we multiply A over B by its reciprocal, that gives you a multiplicative inverse of 1. That is according to the inverse property of multiplication. Let's have an example. 7 over 4. What do you think will be multiplied to 7 over 4 to give you a result of 1, a multiplicative inverse of 1? Okay, so we have it 4 over 7. Very good. So this is an example for multiplicative inverse. Yes, inverse property under multiplication. So again, according to its property, please do not forget, it states that the product of, take down note, it states that the product of any number and its multiplicative inverse is 1. So the multiplicative inverse of A over B is B over A. For 7 over 4, we have 4 over 7. What about this one, number 2? 3. What is the multiplicative inverse of 3? Of course, it's reciprocal, 1/3. That gives you 1. Okay? So that is under multiplication. What about for addition, sir? Yes. What about for addition? For a while. Multiplicative inverse, of course, we also have um, for addition. For addition, according to addition, what will be, what is the additive inverse of this one? Familiar with the word additive inverse? That gives you 0. Of course, that's negative A. So, according to the inverse property of addition, additive inverse is the opposite of the expression. So, A plus negative A is equal to 0. So, you are going to combine or add or combine the opposite or its opposites that will give you a 0. So we apply this one in integers, right? When we apply the additive inverse of the numbers, then when we try to combine them, the result will be 0 or the numbers will be eliminated. So example, let's have an example for last 5. Of course, what is the additive inverse for 5? -5, which gives you 0. So it's opposite. When you combine any number by its opposites or any expression by its opposites or opposite rather, then it gives you 0. That is the concept of additive inverse or inverse property for addition. Another example, of course, if I have here -10, of course, its additive inverse will be 10. And that gives you 0 as a result. So do not forget about this one because this is very helpful in solving integers, in solving rational numbers, and even in algebra, simplifying expressions, and even solving for equation. So this will help you a lot. Okay? Yes, exactly. So that's it. That ends our discussion about the properties of real numbers. Do not forget about it, okay? And please do share and click and subscribe my channel if you like it, and share this channel and video discussion to your friends out there, especially those who are doing the online classes and even those who are answering the modules. So please do not forget to subscribe my channel, and always remember that math is, or the essence of mathematics is not to make simple things complicated, but to make complicated things simple. Always remember that math is fun. Have a good day, everyone. Thank you for listening.